Welcome to this Eclipse tutorial series. My name is Michael Traeger, and I created these videos while finishing my master's degree at Duke University. This tutorial series was funded by the Medical Physics graduate program at Duke University. These tutorials will be focused on providing an introduction for students in the Duke Medical Physics graduate program with respect to a project they will complete during their radiation therapy class, but can be extended as a useful tool for any beginner Eclipse users. As a disclaimer, these videos are not meant for use as guides for clinical applications, including treatment planning on real patients, rather as a good starting point to familiarize new Eclipse users. I'm not affiliated with Varian Medical Systems or with the ARIA software at this time, and am by no means an expert user. In this video series, I will cover the basics of the Eclipse interface, getting started with the treatment plan, contouring strategies, basic 3D planning, IMRT planning, and how to analyze plans. I'll be working with Eclipse version 13.6 and ARIA version 13.6. Alright, let's get started. This is the fourth video of the Eclipse tutorial series, Basic 3D Planning. In this video, I will discuss basic treatment planning strategies, an introduction to 3D treatment planning, how to include add-ons, how to calculate dose and modify beam weightings, and how to normalize the plan. Before we get started with making a plan, it's important to discuss some basic strategies for treatment planning. Let's do so by looking at a prostate plan. Rather than using the prostate phantom we used in previous videos, we'll use this anonymized patient with physician-delineated contours. The goal of treatment planning is to deliver a desired prescription dose to the entirety of a tumor, while limiting the dose to healthy tissues to the best of our ability. As we can see here, in the current plan we have a very conformal dose distribution, and this limits the dose to surrounding healthy tissues such as the bladder and the rectum. Understanding PDDs is important for being able to do this effectively. As we know, we get a maximum dose at a certain shallow depth in tissue that depends on the type of the beam and its energy, after which the dose delivered declines at a rate also determined by the type and energy of the particles. Therefore, we need to use the principle of superposition to deliver a desirable dose deeper into the body. To better understand this, we can visualize what happens with the addition of different amounts of beams. Let's look at a plan that has only one field. With only one beam, we can see that the dose is very high near the surface of the patient, and it decreases with depth. If we draw a line profile through this beam, we will recreate a PDD for this beam. So we come up to the top, select the dose profile option, and then drag and drop to make a line profile. So we now have a PDD for this beam. As you can see, our max dose is at about 1.5 centimeters, after which the dose decreases, which makes sense because we expect our max dose to be at 1.5 centimeters for a 6x beam, which is what we have in this plan. If we add another beam, however, we start to see something that resembles an acceptable dose distribution. This is because we need less fluence, and consequently less dose, from each field to reach the prescription dose of our target. We now have those same PDDs, however, since we have two beams contributing to the dose, they can add constructively to allow a higher dose at the center than at the surface. Let's draw that dose profile from the same beam as we did before. In blue, we have the total PDD. So as you can see, we have that same shape, but then where the beams are superimposed, we have a large increase in dose. If you look at the red curve, however, this is the original PDD, so that does not change. We're just seeing the effect of superposition. Let's now look at a plan with three fields. With three beams, we now see the effects of superimposition even more pronounced. With four fields, we see that our dose distribution is hottest at the center where our target is. A four-field plan, also called a four-field box, was the standard of care used to treat prostate for years. With modern imaging techniques and delivery advances, however, we can improve further. Here we have a 9-field plan. IMRT prostate plans can have up to 11 beams. Now we have a great dose distribution with acceptable doses to the critical structures. You can now start to understand how the more beams we add, the better our distribution can get since we have more superimposed beams. Consequently, however, the more beams we have, the more areas overlap in regions where we want to limit our dose. Also, the more beams we use, the longer the treatment will take, which increases the setup and delivery time and results in the patient being on the table longer. This can lead to more motion and more patient discomfort. All these aspects must be taken into account when creating your treatment plans. Now that we have a basic understanding of how to create a desirable dose distribution, let's make a plan from scratch. We will start by inserting a new plan into our course, which if you remember is just a collection of plans. So we'll go to Insert, New Plan. We'll choose the Eclipse tutorial course, which we currently have open. Let's choose PTV 76 for our target volume. Our primary reference point at this point does not really matter, so we'll choose isocenter. We'll choose head first supine, because that's how the patient was CT simmed. Let's name this plan tutorial. Everything else here looks okay. So we'll now be prompted to insert our first treatment field, but for now let's hit cancel. So we now have our plan created. As a refresher, on the left-hand side we have all of our registered images, we have all of the contours, we have our reference points, our dose, and our fields. On the bottom we have a lot of useful features such as the fields and the dose prescription. So let's start by inserting our dose prescription. Since we're doing a conventional treatment, let's assume our physician prescribed 200 centigrade for 39 fractions. So we'll enter 200 centigrade, 39 fractions, and we'll come up with a dose of 78 gray. Now let's insert our first field. To do so, go to the Insert option on the toolbar and select New Field. We first have to choose a treatment machine, and then we'll follow the red dots until we have created an acceptable field as we mentioned in the previous video. So let's choose the red machine. So we'll follow the red dots, we'll go to Geometry. Let's choose a static technique, follow the red dot again, and let's use a 6x energy. So we've now done everything we need to create the beam, we'll select OK, and there's our beam. We can turn various structures on or off by clicking on the boxes here on the left-hand side. So let's turn on the body to help us visualize. We can now go into the Fields option and we can play around with the field. So we could change the gantry rotation, can also change the collimator rotation and the couch rotation. So a useful thing you can do is right-click on the 3D view and select Set Beam's Eye View to Field 1. This will give you a beam's eye view of the field. So now if we change the collimator rotation, we'll be able to visualize it on the screen. Since we're already looking at our beam's eye view, let's customize our first field to be more conformal. We can manually edit the field size by dragging each dimension of the field, like so. So right now, since our bladder is blocking the prostate, let's turn it off so we can see the prostate better. An easier and more accurate way of shaping the jaws is to right-click on the field and select Fit Collimator to Structure. So I'll right-click on the field, Fit Collimator to Structure. We are now able to enter a margin. For now, let's just do 1 centimeter. We'll leave this as use asymmetric jaws, and we'll select Fit. So now our jaws are perfectly fit to this structure with a 1 centimeter margin. Let's add 3 more fields and recreate the 4-field box plan that we saw earlier. If you remember from the last video, we can simply copy and paste each field to copy all of the parameters from the original field. So I'll do so now. So now we have 2 fields, 3 fields, and 4 fields. Let's now change the gantry rotation so that we mimic the same plan as we saw before. So we'll have one at 0 degrees, one at 90 degrees, 180 degrees, and 270 degrees. So we now have a 4-field box. Let's do the same thing that we did with the first field and fit each of the collimators to the structure. And let's use that same 1 centimeter margin. So rather than right-clicking on each field, we can simply select the field and it'll change fields for us. Now we have 4 fields and all of them are fit to the structure with a 1 centimeter margin. Now that we have our 4-field box, let's calculate the dose and see how our plan is doing. To do so, we can click this button up here that says Calculate Volume. We are now calculating the dose for each of the fields. We now have a dose distribution for our plan. I like having the dose color wash on because it helps you visualize the plan, but another option, which is more common, is to use isodose lines. So we can right-click on the dose, select Dose Color Wash, and turn it off. So now we can see all of the isodose lines for our plan. For now, let's turn the Dose Color Wash back on. To get a better conformity, let's try adding MLCs. To do so, we can right-click on the field and select New MLC. We can now see the MLCs present in our 3D beam's eye view. Let's turn off the dose color wash so that we can see it better. Similarly to how we shape the jaws to the target, let's do the same with the MLCs. So we can right-click and select Fit to Structure. Now let's select 1/2 centimeter margin. If we optimize the collimator jaws, this will optimize the jaws to just outside the MLCs so that they're as tight as possible. So let's do that. And select Fit. So as you can see, now our MLCs have been shaped to the target. Let's do this for all of our fields. So remember, we'd right-click, New MLC. Our beam's eye view will now switch to those MLCs that we just added. And we'll do that for all the beams. Like we did before, we'll right-click, Fit to Structure, use a 1/2 centimeter margin, optimize the collimator jaws, and fit. If you remember before, we do not have to exit the screen. We can simply click on the next MLCs and continue. Now all of our MLCs are conforming to our target, and all of the jaws are as tight as possible to be outside of the MLCs. Since we've edited the beams, we're going to have to recalculate our dose, so let's do that. Let's turn back on the dose color wash to see our dose distribution. Might not be very obvious, but we can notice now that the edges of our target have better conformity since we're not restricted by the jaw dimensions. We can even further tweak the MLCs by selecting the Select MLC options. So if you have our MLC selected, we have Select MLC Leaves. So we can now drag and drop each MLC manually. As I mentioned before, every time you edit the fields, you'll have to recalculate the dose. I personally prefer to do the automatic shaping, but you can play around with what you like. Also up here, we have a shortcut to fitting the structure. So we'll fit it as we did before. We can also select solid leaves to help us visualize better. We can deselect all leaves, select all leaves, and lock the leaves. Now that we have a pretty basic plan, let's talk about some other strategies. When we insert a field, it automatically gets aligned to the target volume, but what if we want to change what the field is centered on? We can do this by right-clicking on the field and selecting Align Fields To. So we could select to align the fields to a structure projection, a reference point. So let's choose a structure and do the femoral head just for fun. One thing to notice is that it said Align Grouped Fields. Grouped fields are all fields that are currently checked down at the bottom over here. If we want to move an individual field or select a group of fields, we can pick and choose which fields are grouped. So for now, let's just move the fields back to the original position. Since they're grouped, they will all move at the same time. So let's move them to the isocenter. To further modify our beams, there are a few add-ons we can use. To insert an add-on to a field, we can right-click on the field and select Properties. We can then go to the Accessories tab. So all the accessories commissioned for the current treatment machine will show up here. So let's add a wedge to show you how this is done. So in slot 1, click the drop-down. Let's use a 30-degree wedge that's specified on the right. The right side specifies where the heel is. So we can select Apply. Now as you can see, on field 1 we now have a wedge. Another useful tool is field weighting. In our current plan, our right and left lateral beams need to penetrate a larger distance of tissue than the AP and PA beams, including bones, to reach the target. Therefore, it might be helpful to weight the beams differently. Prior to changing the beam weightings, we must recalculate the dose. So let's do that now. Now that we have our updated dose, to weight the beams we can go into Planning and select Field Weight. Here we can manually change the weightings of the fields. We can use the slider bars or manually type in the weightings that we'd like. So if we drag these slider bars, all of the weights will change to make sure it's 100%. We can also select the interactive Apply. Now, as we slide this and let go, it'll show us directly what happens in our plan. So let's equalize them again. We can also lock a certain field's weighting. Now, if we change the weightings of another field, the field that we locked will not change. However, the others will. Since we have a pretty basic plan, let's use 35% for our AP and PA beams and 15% for our lateral beams. To do so, we can simply type in a number and select Enter. Now that we have our 35% on our AP beam, let's lock that. Let's do the same for our PA beam. Lock that. And now we have a lot more dose in the center, and we have less hot spots at the edges. We can now close this. Once we have an acceptable dose distribution, one of the last tweaks we usually use is normalization. This allows the user to scale the monitor units in such a way to achieve a desired coverage or normalization level. So normalization is in the Dose Prescription tab. Let's open the Plan Normalization mode. I discussed all of these in detail in the first video. Let's try a couple of these normalization techniques. First, we'll use the most common one. this fourth option. Let's set our normalization such that 100% of the prescription dose covers 90% of the target volume. Let's apply it, and now let's look at the isodose lines. To help us visualize better, let's turn off the fields. So since our prescription normalization says 100% covers 90% of the volume, our 100% isodose line, which is the yellow here, is only going to cover 90% of the target. So as you can see, this 10% is being left out. And this is throughout all of the slices in 3 dimensions. Let's choose a different normalization mode. Let's change it such that 100% of the prescription dose covers 98% of the target volume. We can now see that the dose exploded all over the place. So up here, where we don't have the target, we now have dose, because our system is now forcing 98% of the target volume to get 100% of the prescription dose. We're getting a lot of dose up here because this is where we had that wedge, if you remember. So when we're using wedges and other add-ons, we should be careful with them. There are many other tricks and tips to treatment planning. I mentioned a few of them, but as you see other individuals make plans, you will adopt bits and pieces until you come up with your own style. Thank you for viewing this video in the Eclipse tutorial series. I hope you now understand how to create a basic 3D treatment plan and how to use normalization effectively. In my next video, I'll teach you how to create an IMRT plan, as well as discuss inverse optimization. Thank you, and I'll see you next time.